Alrighty, are you ready for some mathematics? Alright, the trig form of complex number, day 4. We're going to be calculating roots now of complex numbers. Alright, so in order to establish a few things, I'm going to have to get you to buy into two basic concepts, one of which is going to be on this slide, the next one's on the next. So here we go. Okay, so if I ask you how many solutions an equation has, there is a fairly easy way to do it, especially if you're looking at a polynomial sort of thing like this. Okay, of course, as soon as you see that 6x squared, and that's the highest power you see, you know this guy's got two solutions. Easy enough. Likewise, x to the 8th minus 1, even though it's this compact little equation, since I'm dealing with x to the 8th, I eventually am going to have 8 solutions. You know, likely some of those are going to be complex, but there's going to be 8 of them. Okay, basically nothing changes the second I start looking at some negatives or some imaginaries here. Okay, I've got x to the 3rd, so basically what I'm doing is taking the cube root of negative 27i. Now that seems kind of preposterous right now, but that's kind of what this lesson is going to be all about. But since I am dealing with x to the 3rd, I am going to be dealing with 3 separate solutions to that equation, so effectively I have 3 roots for negative 27i. And then basically these next two are just to kind of drive the point home. Even if I start making a more complex number looking sort of format instead of the pure imaginary number here on this example, x to the 4th eventually gives me 4 solutions. Likewise, x to the 5th gives me 5 solutions. Alright, so basically, again, to do this, I'm taking the 5th root of both sides, sort of, and in some kind of weird way, which is what we're about to do, we can figure out 5 different solutions. So any complex number has n distinct nth roots. So if I want the 28th root, I'm going to find 28 different answers. I promise I won't make you do something that much, but there you go. Alright, so if you can buy into that idea, that's step 1. Hopefully that made sense. Alrighty, so now that brings us to this formula we have for the complex numbers, which is actually doing De Moivre's theorem backwards. Although it looks a lot messier because, well, quite honestly, doing a power isn't such a complicated thing. Doing a root usually ends up being worse, and basically here it is. Worse. Alright, but anyway, so for z equals r, blah, blah, blah. Okay, the nth root, okay, hopefully I highlighted that s sufficiently so that you realize that there is more than one. The roots of z are here. Okay, so the nth root of z is, we're going to do the nth root of our r. Again, notice we have trig form to work with. Okay, now here's the other thing I need you to buy into. Okay, again, so instead of a theta right here, we need to take theta, and then we need to add 2 pi k, and then we're going to divide it by n. Again, the n is the same n as right here. So those two are going to match. In fact, all 3 of those match, or if you even want to go for it, all 4 of those match. But whatever the case is, those n's are all the same. Okay, now the k values here, we're going to start using k equals 0 first, then we'll use k equals 1, 2, etc., all the way to 1 less than whatever our n value is. And hopefully that makes sense, because our n value is, let's say, 4, we're going to use 0, 1, 2, and then 3, which does include 4 different values, so that's the 4 different roots. Okay, so what I need you to buy into here is, as we keep going around the circle here, whatever theta is, basically because I'm going to divide by that n value, I need to go around the circle multiple times, so then by dividing by n, I'll get something that actually makes sense, and actually get a different angle measure, and therefore a different root each time I do this. Basically, you kind of need to do this a few times so that you kind of get used to the idea, and then it kind of makes sense, and hopefully through the course of these next couple examples I do, it will make sense. But basically this 2 pi right here is just going around the circle multiple times before dividing by whatever our n is, in order to make sure that we have distinct separate roots. Alright, if you can buy into that, great. So here we go. The following problems, we will find the roots, represent them graphically, and then write the roots in standard form. Alright, brace yourself, here it comes. Okay, sort of hopefully ease you into this by doing something that's not quite too out of control. Alright, we're going to find the second roots of 12 cis pi over 4. Okay, so part A is find the indicated roots. Okay, so now we have that big messy formula to work with, but here it is. Okay, notice we have the k values we need to use. So I'm going to start out with k equals 0. Sounds like a good place to start. Alright, and then so, again, what I want to do is, I'm doing the second root, so right now I want to take the second root, which again, that 2 you really don't have to write, of our r value, in this case 12. And then, again, just to save a little bit of space, I'm going to do the cis, and unfortunately it's a big nasty sort of thing, so I need to do the original theta, in this case pi over 4, plus, again, a full circle times our k value. In this case it's actually 0, so that'll actually cancel itself out. And then we're going to divide through by whatever our n is. And again, the n is the type of root we're taking. In this case, it's the second root. Okay, so that's basically us plugging things into the formula. Or I guess it was me, it wasn't really us. Alright, so anyway, simplifying this mess down, the second root of 12, it quickly simplifies to 2 root 3. And then again, this mess, the 2 pi will cancel out. And so I have pi over 4 over 2, which is pi over 8. So now I have cis pi over 8. Okay, so there's one of my roots, but of course, since it's a second root, I actually have 2 of them defined. So basically I just go to my second k value, in this case is 1. Okay, so now here's my first root, and here's my second root, so this is my last one. Alright, so again I'm going to do a root 12, and then cis, and it's really all the same, except the 0 is going to become a 1. So now I've got pi over 4 plus 2 pi times 1, all over 2 again. Okay, so not a whole lot's different. I've still got a 2 root 3, I've still got cis, and then now I'm adding 2 pi once. So really again that's 8 pi over 4. So 1 pi over 4, 8 pi over 4 is 9 pi over 4. 9 pi over 4 over 2 is 9 pi over 8. So then there's my second root. Okay, hopefully I didn't be too fast with that. Adding the fractions is the other thing, but there it is. Okay, I think we've done that once or twice in class. But there's our roots. Alright, so basically continuing with the problem. Okay, now I've kind of transferred those 2 values we found down here. So part B, represent them graphically. So here's the 2 things we just found. Okay, so first of all, our R value is 2 root 3. So one thing that's going to be important to know is that 2 root 3, or root 12, if you want to go to the unsimplified form, is approximately equal to 3.5. It's actually 3.46, whatever, but I think for a hand-drawn graph, 3.5 is good. So I'm basically just going to do 4 tick marks in each direction of my little grid right here. Alright. Okay, and again, the pi over 8 and 9 pi over 8 are basically just angle measures. And what I can think of here is a circle of radius roughly 3.5. Alright, so I'll change colors for effect here. Okay, 3.5 of course is there, 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 and there. And of course these aren't very evenly spaced, but I will do my best to draw something that looks vaguely like a circle. Wow, that was bad. Okay, but if you use our imagination, we can see that that's kind of a circle almost. Kind of, sort of. Not quite, but anyway. Alright, so here we go. So there's a circle, radius 2 root 3. And I've got to do pi over 8, and then 9 pi over 8 is my 2 angles. Well, pi over 4, of course, is like a 45 halfway. So pi over 8 is half of pi over 4, so that means go about halfway down the circle, and there I am. So basically right there is my first root, which is 2 root 3 cis pi over 8. Okay, and hopefully it's not too much of a shock here. 9 pi over 8, notice that's a little bit more than 1. So if I go a little bit more than 1, I'm going to be about here, and what I actually have is something that's straight across from the pi over 8. Okay, and in case that's messing with you, notice that pi over 8 plus 1 whole pi would get us to 9 pi over 8. So I should be directly across the circle. Alright, but that being said, now I have 2 root 3 cis 9 pi over 8 right there. So there's the graphical version of these. Notice how the 2 roots cut the circle into 2 even pieces. Coincidence? I think not. Alright, now moving on to write these guys in standard form, what we basically need to do is just kind of work them out. Alright, so going back to my pretty red, I've got 2 root 3 cis pi over 8. Alright, and so basically again, just for the sake of argument here, I'll just write it out. 2 root 3, remember you have to break it into pieces. So instead of cis, I'm sorry, there's cosine. That's an O, not an I. Alright, got cosine pi over 8 plus I sine pi over 8. And unfortunately, pi over 8 is not a unit circle value that I can work with nicely, so I'm going to resort to the calculator here and round to the nearest tenth. By doing that and then distributing the 2 root 3, which again is probably best turned into a decimal first, and then kind of smashing all the decimals together, gives me something that rounds to 3.2, and then something that rounds to 1.3 with the I on it. Okay, again, if you left all those decimals in your calculator and squared them, you should eventually get back to this thing, converting it back into trig form, but that's kind of messy to do. Alright, same thing with the other one, 2 root 3 cis of 9 pi over 8. Again, going through the same basic process of breaking it up, distributing the ecadecimal into the ecadecimals should give you something, and hopefully right now this won't be much of a shock. Okay, I've got negative 3.2 minus 1.3i. Okay, so again, if it's positive 3.2 and then positive 1.3, and again, if I'm going the exact opposite direction, hopefully negative isn't too much of a shocker for you there. Alright, so there's basically one with a second root, so not too bad. Let's do one that's a little bit worse. Alrighty, let's try to find the fourth roots of 8 parentheses negative root 3 plus I. Alright, well, first thing first is I don't have trig form, so that's probably something I need to do. Alright, so I'm drawing a quick little sketch here, okay, and maybe even distributing first. This is negative 8 root 3 plus 8i, if that helps. So horizontally I'm going negative 8 root 3 out to wherever you feel like, and then I'll go up 8, that's an 8, and again finish my triangle like that. And again, hopefully you can quickly identify those as nice unit circle values, therefore giving me a 16 for my hypotenuse, radius, whatever you want to call it. Alright, and again, basically what that gives me is a 30-degree or pi over 6 angle. Again, this is a formula that's built on radians, so I'm going to work in radians. So the angle it takes me there, since I'm left with pi over 6 here, is actually 5 pi over 6. Alright, so pretty quickly, I now have my trig form of 16 cis 5 pi over 6. Alright, so there's my trig form, and let's even label that, it'll be fun. Alright, but again, that's only not even half the battle, that's one little fraction of the battle. Alright, so now, again, I'm doing the fourth roots, so I need to run k equals 0, k equals 1, k equals 2, and then k equals 3 to get my 4 separate roots. Okay, now starting with 0, okay, again, I'm doing a fourth root, so I want to take the fourth root of my r, which is 16, and then again cis of that big nasty sort of fractiony thing, 5 pi over 6 plus 2 pi k, in this case 0, and again now my denominator is 4 because again I'm taking a fourth root. Those two numbers should always match. Alright, and then just continuing this whole process. Alright, again this cancels nicely, and if I have 5 pi over 6 over 4, it's really 5 pi over 24. At the same time, the fourth root of 16 is 2. So this becomes 2 cis 5 pi over 24, and there's the first of my 4 roots. Okay, just doing the second one now, and I still have the fourth root of 16, and really at this point, if you just wanted to write a 2 right there, because you know what it's going to be, go right ahead. But now I've got cis, again, big icky fractiony thing, 5 pi over 6 plus 2 pi times 1 now, and it's still all over 4. Alright, and working that mess out gives me 2 cis, and now it works out to be 17 pi over 24. Okay, again, because I'm adding 2 pi, so it's really like 12 pi over 6. 5 over 12 is my 17. Dividing gives me the 24. Alright, so there's that. Just to save you the effort of watching me do this again, if we just continue the process here, I get 2 cis 29 pi over 24. And then my fourth one ends up being 2 cis 41 pi over 24. Okay, if you really want to see me do those, grab me in class and ask me to finish it, and I'll be happy to do so. But there's at least our roots. Let's move on to the graph. Alright, so here's the graph. Alright, so, okay, a couple things need to take place. One of which is, well, I have 2, so that's something I don't have to worry about a decimal, so I'm going to have a radius of 2 circle going all the way around. But before I get there, the angle measures I have are in terms of 24ths of pi. Okay, so I'm going to neglect the pi for a second as I do this, but, okay, so over here at the start, I basically have 0 24ths, so no big shocker right there, I hope. Okay, now when I get up to kind of the pi over 2, that's basically saying 1/2 of pi, and again, if I'm talking 24ths, that's really 12 24ths. Okay, as I get to the negative x, I have basically 1 pi, so that means I have 24 24ths. Okay, as I get to be straight down here, okay, well notice every 90 is basically a 12 24ths, so 12 more 24ths onto here is going to give me 36 24ths. And then taking that same logic back over here to our starting point means we have 2, which is 48 24ths. Okay, so looking at those, we can probably place these various 24ths of pi in at least reasonably good locations. Okay, so moving on now to my 2. Okay, my radius at 2, so 1, 2, sounds about good to me. 1, 2, etc. And hopefully I can evenly space these reasonably well so we can draw a pretty decent circle. Alright, so there's my 2 on either direction, and hold your breath everybody, here we go. Reasonable. I think I can keep my job. Okay, so 5 24ths. Okay, well 6 24ths would be halfway exactly, so 5 24ths is going to be down just a hair. So I'm going to put that guy right there and call him 2 cis 5 pi over 24. Alright, and I'll draw this nice dotted line because that'll help later get things in a nice position. Okay, same thing kind of going around here. 17, maybe it's not quite as obvious, but 18 would be exactly halfway between 12 and 24, so 17 is just a smidge short of the 18, so that'll be about right there-ish. That looks kind of like a nice angle. Alright, so basically right there I'm looking at 2 cis 17 pi over 24. Okay, hopefully not too much of a shock since I'm doing a 4th root. I'm basically chopping the circle into 4 pieces, and if I do that I end up with some nice right angles. Alright, moving on to the 29. Okay, again, 30 would be dead halfway between here, so I back it off a smidge and get to my 29, and notice again how that lines up. Now again, you can't really totally assume that just from the hand-drawn thing, but again, if I go from 5 to 29, that's exactly 24, and that's the fraction of the circle I'm working with, so again, it is exactly 1/2 of a circle by adding 24 24ths. So 2 cis 29 pi over 24. Make sure that looks like a 9. Okay, and then I'm sure you don't want to listen to me explain it again. Right there would be my 2 cis 41 pi over 24. So again, notice the 4th root chops it into 4 even pieces of the circle. And again, so hopefully it's being a little more clear now that when I'm adding that 2 pi k on repeatedly, it is to get me in a position so that when I divide by the n, it lands me in a very, very nice chopped up single circle to get all of my roots. Okay, so hopefully that made sense. Alright, then doing this in standard form again, basically all I would do is type these guys in like I did in the previous problem, and if you want to do that just to double check what you got, basically my first root works out being 1.6 plus 1.2i, again there's a little bit of rounding going on there. Okay, the second one, and hopefully this starts looking kind of interesting, I get negative 1.2 plus 1.6i. Alright, as I do the third one, I get a negative 1.6 plus, oops, I'm sorry, not plus, minus, that's a minus, that's a minus. Undo, undo, undo. Alright, minus 1.2i. And then lastly, I would get a 1.2 minus 1.6i. And if you pay attention to the signs here, notice how the first one lands in the first quadrant, second in the second, third in the third, etc. So it does pretty well look like we do have things in the right positions as we do that. Okay, I know that's a big truckload right there, and it's a little bit nasty to deal with, but that is what it is. Please ask me in class any questions you have.